Alright, in this video we're going to start talking about curve sketching. So there are some guidelines for analyzing the graph of a function, and I'm going to give them to you right now. So the first thing is we need to find the domain and range. Now remember, the domain is all the x values that can be used in the function, and the range are all the y values that are used. Once we found the domain and range, we're going to find the x and the y intercepts. We're going to find any vertical and horizontal asymptotes, as well as find any symmetry of the graph. Then we're going to find critical points and intervals where the function is increasing and decreasing. Once we've done that, we're going to determine any local maximums and minimum points, Once we've done that, we're going to determine the concavity and find points of inflection and then lastly, we're going to make a rough sketch of the curve. So once we've identified all the things above, we're just going to plot those points and graph. So let's look at our first example. Example 1. We are going to take the function f of x, which is equal to x cubed minus 6x squared plus 9x minus 2. So from what we learned earlier in this chapter on applying the derivative, we're going to need to find f prime and f double prime. We need to take the first and the second derivative so we can find some of those important points that were listed in the guidelines. So let's start by finding f prime. We can bring down the 3 on the x cubed, get 3x squared minus, bring the 2 down, so get 12x plus 9. And then while we're at it, let's also find the second derivative. So we bring the 2 down from the 3x squared, get 6x minus 12. Now, remember, to find critical numbers, we're going to want to take the first derivative and set it equal to 0. So let's do that. We've got 3x squared minus 12x plus 9 is equal to 0. I do notice that each term is divisible by 3, so I'm going to take a 3 out, factor it out. So 3 times x squared minus 4x plus 3, that's equal to 0. And we can do a few different things with what's left in the parentheses, but I believe this is easily factorable. We need to figure out what numbers multiply to make 3 and add to make negative 4? Well, negative 1 and negative 3. So we're going to have 3 times x minus 3 times x minus 1 equal to 0. The only way this can equal 0 is if the two binomial factors equal 0. For the first binomial to equal 0, x would have to be 3. And for the second one, x would have to be 1. So our critical numbers are going to be at 1 and 3. Let's also set our second derivative equal to 0. That's going to help us determine on those intervals for these critical numbers if we have a max or a min, and in what intervals are we decreasing and increasing. I notice on that second derivative both terms are divisible by 6, so I'm going to pull that out right away. We're going to have 6 times x minus 2. If we set that to 0, the only way that could equal 0 is if x is equal to 2. Now those are all important parts here. Let's find our y-intercept. That's actually real easy. Our y-intercept is going to be whatever term does not have a variable with it. And in here, we've only got this last term, so our y-intercept is at the point 0, negative 2. Now this function has no asymptotes, so what that means is our domain and range goes from negative infinity to positive infinity, and that's for both domain and range. And I know there's no asymptotes because I don't have any x value in the denominator of any terms. I also don't see any radicals or anything that would create a need for an asymptote. Now the intervals we're going to look at, we're going to take our critical numbers in mind. We're going to look at the interval from negative infinity to 1, the interval 1 to 3, and 3 to positive infinity. Now, test numbers. I would just take and test x equals 0, x equal 2, and 4. So we can determine if these intervals are increasing or decreasing. So we're going to take and put 0 into, so let's plug these values into our first derivative and see what we get back. So if we were to just plug 0 into f prime, we would get 9 back. Which, since that is bigger than 0, since 9 is greater than 0, that means this is increasing on that interval. If we were to put a 2 in, well, 2 squared is 4, times 3 is 12. 12 minus 24 is negative 12, and negative 12 plus 9 is negative 3, which is less than 0, so it's decreasing on that interval. And then we plug 4 in. 3 times 16 is 48. Minus 48 is 0. And 0 plus 9 is 9, which means we are increasing on that interval. Okay, so we've got a lot of good stuff. We know where we're increasing, we know where we're decreasing, we have a y-intercept, we know our domain, our range, our critical values. We just have to now determine what those points are. with increasing and decreasing, we can know if they're maxes and mins. And then we know we have a point of inflection at 2. We just need to know where specifically that's at. Since I've run out of space, I'm going to go to a clean page. But let's keep all this information in mind. So we're going to now determine what are the maxes and the mins, and what is that point of inflection. So we, as a reminder, critical numbers we know are at x equals 1 and 3. And we know we've got another important point from our second derivative test for a point of inflection at x equals 2. We just now need to determine what are those points. Like, what's the y-coordinate there? So to find the point of inflection, we're going to take 2 and we're going to put it into the second derivative. Correction, we're going to actually take 2 and we're going to put it into our original function. So if we put 2 in for x cubed minus 6x squared plus 9x minus 2, we would get 8 minus 24 plus 18 minus 2. That's going to give us a point of inflection at the point 2, 0. So that's going to be an important point when we're sketching. Now our critical numbers we're going to take and plug into. We're going to plug those critical numbers into our original function to find maximum and minimum values. So we know we've got a critical number at 1. If we plug 1 in to our original function, we're going to get 1 minus 6 plus 9 minus 2. That's going to give us a point at 1, 2. And then if we put 3 in, we get 27 minus 54 plus 27 minus 2, which is going to give us a point at 3, negative 2. So I'm just going to write down some of the stuff we've got here on the left. So we've got a point of inflection at 2, 0. We know that. We have a point at 1, 2, which was from an interval that was increasing to decreasing, which makes this a maximum. And we've got a point at 3, negative 2, which is a minimum because it was going from decreasing to increasing. And just as a reminder, the intervals that we were increasing on, we were increasing from negative infinity to 1 and from 3 to infinity. We were decreasing from 1 to 3. We know we have a y-intercept at 0, negative 2. You've already got all this written down. I'm just rewriting it so I have it here. And we know the domain and the range is negative infinity to infinity on both. That doesn't really matter right now. So let's make a rough sketch of what we've got going here. Now, we don't have to be exact when we're graphing this. We can put a point, we know negative 2 is below the origin. We can put a point at 0, and as long as we label it 0, negative 2, that's fine. We can also put a point on our x-axis. Now, that one's not really in a great spot. Maybe right there. We know that's at 2, 0. That's our point of inflection. We know we've got a point at 1, 2, and a point at negative 2. Not negative 2, at 3, negative 2. Now we know from negative infinity to 1, we are increasing. So it's going to look something like that. and then we decide to go down, and at this point of inflection is where our concavity decides to change. And at 3, -2, we switch from decreasing to increasing. So we've got a rough sketch of our curve. That's going to leave it for this video. We'll do another example in our next video.